Yeah, so
Just so that.
yeah, so I think that should be good enough for most purposes. I mean, if you want to download the 3.2.4, that's fine.
I had an old version and I realized it.
Yeah, me too, actually.
So what happens if you have an old version?
I don't know.
Is let's find out.
3.2.4. This guy, right?
Right. Our version was like
Good job.
Yes.
My computer's forcing me to
suggests us to
Windows 10.
download it again.
Upgrade to Windows 10.
Windows 10. Do you have any
It'll take a while.
concerns about that?
I mean, if you have Windows 10, I don't have any concerns because I don't use Windows.
Yeah.
But if you use Windows, then you might want to, you know.
Why don't you search for the version of R that works with your operating system?
Exactly.
Oh, I haven't upgraded yet. I have to do it like in the next couple days apparently. But
Oh, so, okay. So you can do it over the weekend.
yeah.
We're not going to be doing R, we're just talking about how to download it, okay?
Okay. I just downloaded it.
Okay. So you just download and install R. And then the next thing we're going to do is, after downloading and installing this package file, let me try it just to show you. Continue, 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 agree. It's like any other package. Install, enter password, preparing. I have an older version, so let's see what it says.
Defaults are fine, right? Not customized.
Yeah, no customize, just go with the defaults. Install time less than a minute. So we have a less sugar version here. If you want to add sugar, please go for it. I guess that will confuse the people who are watching the video afterward. Sufficiently confusing. In the meantime, if you already have R, go to Google and search for R Studio. One word. R Studio download. Alright? And this should bring you here, download the first link that comes up, download R Studio. Click on that. And then you don't want to download the server, you just want to download the client. And the way to do it is, it gives you multiple options here. Choose the one that applies to you. So RStudio 0.99 for Windows or for Mac OS X. Download that.
Vishal, sorry, I was behind. I just finished the installation for the
R?
R2.24. What was this again?
Wait, 3.24R.
3.24, yeah.
And then
So
you
now
go
we're
to
in-
Google and search for download RStudio.
Download RStudio. Okay, got it.
Right? And then go scroll down to the bottom of the page, and right here where it says installers, download the one for your platform. In your case, it will be Mac OS X 64-bit. Alright? This one, the second link. If you're Windows, it's the first one. Okay, so installation was successful for me as well. I already have RStudio, but for the heck of it, I'll do it again. Just for the heck of it. Okay. So we're good? Our studio installation.
Wow, it's like 7 minutes now, and that's gonna take a long time. RStudio.
No, it's 60 seconds.
It says 7 minutes.
Yeah, mine is still downloading.
5 minutes now.
Oh, you can see this. Ah, I wish I could gloat. Here. Now you can see it.
Is there a difference between
did you do that?
i386
Oh, now it says 3 minutes.
and X64? Do you know which one I might be using?
Which one where?
64-bit of R and 386 of R.
64-bit. You have 64-bit computers. Everybody by default nowadays have 64. If you have 32-bit, your computer's old.
Okay.
Is mine 32?
No, probably not. 64-bit started like 6 years ago, 10, almost 6-7 years ago. You can go online and, I mean, you can go check here. I think it's about this Mac should tell you. If you have the Intel Core, they were all 64-bit.
Yeah,
Here. Where does it say hardware?
yeah, hardware where, like,
It should be under your processor name. Actually, just take your processor name and then Google.
Upper graphics. The 32-bit.
32-bit.
Oh, you have a 32-bit?
For a colored LCD, but that's just my color LCD. Is that?
Yeah, that's different. Okay, so
This
yeah,
is
so
400 megabytes.
at some point, you know, whenever you want, you can upgrade to a 64-bit if you want. You don't have to. Most of the software still come in 32-bit as well.
No, but this one doesn't, does it?
R, I think it does. Oh, doesn't it? You can just search for it and see if you have RStudio with 32-bit. Should be there. Hey,
Oh, is that why you put me come in? Thank you.
I know how much you like it. It's not recording you. You can come in front and take them.
No, I'm okay. Thank you.
You don't want?
Sorry, I have to miss.
Okay, all right,
Just take a cookie and leave.
all right. Okay, so everybody downloaded RStudio. Let's install it.
So I shouldn't install this one, I think.
You can try and see if it works. I mean,
Oh, I guess so.
if it doesn't, then yes, open it. So if it complains, it'll say it's downloaded from the internet. You can just open it. Although, I think, do I want to delete it? No, I don't want to close it. Okay, so you want to copy this into your applications to make sure that you have the.
Just drag it into the folder.
Drag and drop it, and if you have an older version, just replace it.
Does it remove all the memory from the previous one? Or it just replaces the application, not your
Yeah.
not your files, right?
No.
From the previous one.
You have an RStudio,
No, I don't.
so then you should be okay.
No, I'm fine. I just wanted to ask in principle.
Yeah, in principle. Yes.
I have it,
So you don't need to do anything. You're fine. As long as you upgrade to the latest version of RStudio will work just okay. Okay, so basically this is it. This is your first step, and if you are here, then you can click on RStudio under Applications. So here, if you go here on Applications on Launchpad, you should be able to search for RStudio. Here it is, right next to R. You just click on that and launch your RStudio. And if you've done everything well, and R is installed, then RStudio will open into something like this. Alright? Yes, open it.
What is R and RStudio?
Oh man. Did it erase my files? No, I didn't. I have two versions. So R is the actual software that runs in the backend, which is the, RStudio is a visual environment that was created to run on R. The actual. If you actually, for the sake of fun, if you want to go and click on R, it has a GUI as well. So if you just click on R, it'll open up into something of a visual. Okay. So this is R as well. So like you can just type here as well R and get WD. So for PWD, the equivalent command is R is get WD. I'm just showing this to you to show that R has its own console, but it's not as nice as this guy here, RStudio, which in essence calls your same console in the back end. It just opens the R console here, and then you can create your files here. It gives you a history of your variables and everything that you have done. And you can show your plots here. It shows you file, environment, packages that you're loaded and that you want to load. It has help here. It's a lot nicer. I mean, you see you have your help available here in the same window. Obviously, in my real estate is a little small because of the projector, but you guys should be able to see a lot more in here. Anyways, so if you've installed RStudio and R, we're good for Monday. Okay. Okay. I'm going to quit that. Save it, fine. Alright. So we're good?
So
Everybody?
can I ask a question? If you have to run R first and then RStudio?
No,
or-
you just open RStudio.
RStudio.
You don't have to deal with R
Okay.
again.
Oh, okay.
And there'll be a way for me to connect to the server from RStudio, even though I have a PC.
There's no need for a server, so when you're installing, this is all local machine work from here on.
Okay.
We're not going to be working on the server.
So I open RStudio and it works actually, so it's running.
It's perfect. Just type get WD in your console and see if it works.
Get WD.
I can do that.
Get WD. First
Here?
typing get WD.
That's good. Doesn't work?
Unexpected symbol. RStudio.
Get WD with brackets. I mean,
Get WD.
here, this command. Over here in your console window where it says console, just type get WD with brackets.
Oh. Oh, okay.
And it should show you the directory you're in, which should be users
Yeah,
slash
yeah.
your name.
Yeah, it works.
That means it's working, that means it's working. Okay? Alright? Alright, so let's now go over to our original, what were we working on, Text Wrangler? Okay. So open your Text Wrangler and open your BedTools file, the practical file.
Is there a latest version we should download on the class website? Or if we have the version from Monday, that should work.
That should be fine. Okay, let's see. There, I mean, I think you should be okay.
It's okay.
Okay, so, we were somewhere, do you remember where we were? Did we cover,
So,
Did-
there was a part where I hit an error.
okay, which one was that?
And that was when we were trying to use the hg18.genome file.
Okay.
So that was like their step 1, step 2.
That was
so
in step 2?
Yeah, so I finished the head, just kind of mixing and merging and all those things.
Okay, intersect, merge, everybody was able to do intersect, merge and all those commands? If not, you can go through it right now, I mean just follow through the practical and if you hit an error, let me know, alright? There's a lot of self-doing in this session as well, so just do your practical and let me know where you get into an error.
I think it was the advanced usage part where it got a little, I guess I'm not advanced.
Don't worry, we'll advance you.
Don't know if that's possible.
We'll get you that status. Okay, so you were able to do genome coverage here?
I think so, yeah.
Okay.
Let me, go back.
So slop done, complement, mask, FASTA, intersect. Were you here? SAMTools index, is that where you were?
Let's see, samples. I mean, I was right at the advanced usage part.
Okay.
BedTools tutorial SAP.
So here?
And I think it's well below that samples.
Where?
It's line 275, or sorry, 283.
Here?
Yeah.
Okay, so where'd you hit the error? BedTools slop?
I think there was already a probes 500 BP, so I didn't do that because it would have just.
Oh,
made the
yeah,
file.
you can remove that and, do it in your
Yeah, but the part was the next one, I think.
complement?
Yeah, so I can
Okay,
try again.
that's probably because of this genome file. Is that what's the error? Let's work on that one. Okay. So, for those of you, do you want me to go through it step by step until we get to here? You have, if you have an error, I can come to you personally and we
You
can.
can summarize, yeah, that'd be good. Like just go through it quickly, then we'll. Because I haven't done my homework.
Okay. All right.
I haven't even understand.
Okay. Okay. getting sloppy.
I'm just more honest about it. That's all.
He can be excused. He has a PI card. Everybody else, not yet. When you're PIs, you can
You can piggyback on me, guys. Just tell me what you need, and I'll
Yeah, he'll just put it forward saying, "Oh, sorry, it was my fault."
But I think a newborn card is good too.
Okay, all right.
I think this is where I had trouble when I
Okay.
left class. Did you guys fix that or?
Yeah, that was BCF tools. Did you send me the email on how to fix that? No, that was Mark or someone.
So that's where I'm at.
Uh-huh.
That's where I last left off. I don't know where that is in relation
Okay,
to.
so that was in the previous lecture. Alright, so that's the last step of the previous lecture.
That's where I am at.
That's where you are.
Yeah.
Okay, so we can ignore that for now,
Okay.
and let's start with BetTools. We're just gonna go over BetTools. Did you attend the class?
Yes.
Okay.
Yeah.
So let's start with the BetTools tutorial. Are you able to open this file?
Yes.
Okay, so let's go to that file. And then start from the very beginning. Alright, ignore everything else and make sure you're in the BetTools, well, I'll just go over the whole thing. Sorry, you'll have to wait.
No problem.
Okay, so the way we start the tutorial is to first make sure that we're in the right directory. Everybody make sure that you have this BetTools demo directory or okay, so first thing, open your terminals, connect. I'm guessing most of you have done that, right? You're in the server.
Yes.
Okay, so we go to data, mghcc, okay. Then we go to, well, your directory, right? And then we have linked to the BetTools demo directory, alright? So everybody's working in this same directory. Are you here? Do you have a BetTools demo directory?
Yeah.
Yes.
Okay, everybody has that. Do you remember how we created it?
ln minus something.
Yes, ln minus s. Do you remember the link command? Do you want me to go over it again?
Going to your direction.
Yeah.
Okay, ln minus s
Uh-huh.
creates a symbolic link. That's why the minus s. Symbolic link for data mghcc bioinformatics class, and then under that we have BetTools demo. Alright? If I just press enter here, it's going to try to create a link. Right now we have a link, so it's going to give me an error.
Got it.
Okay?
Yep.
That's how you created the link.
I don't have a directory, so.
So just create this link. Good then. Just follow this and you'll have a link in, make sure you're in your PWD's, your home directory
Yeah.
within the course.
Yeah.
ln minus s. Were you here in the last class?
No.
Ah,
Okay,
that explains.
that's right. Right. So create your symbolic link in
See, I
your
was
home
helping
directory.
him out, by the way. That's why I said that.
Right, of course. Alright, ln minus s / data mgh bioinformatics class / BetTools demo. If you do it in your directory and press enter, you have a symbolic link. Now if you do ls, you should be able to see your BetTools demo in a different color.
Yes.
Okay,
He's got it.
now we go cd BetTools demo. Okay, in that do an ls. We already have a bunch of bet files and we have some of the other files that you need for this over there. Now we're going to start the tutorial at this point from this exact location. Alright, everybody is in the same directory, so try not to erase anything, no RMs. So these set of commands right here, the curl commands, they are there to help you download stuff off the internet. Basically these are commands that give you these files. This particular tutorial has all these bed files. You see all these bed files here? These ones. The F brain, F intestine, F heart, F kidney, F lung, F muscle, F skin, stomach. All of this are contained as part of this zip archive, Morano DNA1.tgc. If you want to know more about this paper, you can go up and see this is the paper that this data comes from. Okay? Systematic localization of common disease association variation in regulatory DNA. Is that okay?
Yep.
Okay. So curl is just a simple command. It's like, it's saying download this, curl it in from this location. Okay? Once you have a hyperlink that works, it works on HTTPS and downloads in the folder. We extract it, that's what we're saying here. Then we just remove the TGZ file because we no longer need it. We've extracted all the bed files from here. Then we go ls and we see what the files are. Next, we have to load bed tools. Now, bed tools, depending on the version you have, it's basically going to be module load bed tools. I think it's BED capital TO tools dash 2.7 or something. Let's try it.
2.17.
2.17. Module load BED T capital OOLS. Press tab and wait for a second. Wait for it.
So my computer's
Okay, underscore 2.17. Alright, I'm gonna just type that one. Underscore 2 point, and it's not dash, it's underscore 2.17. Okay, just make sure you type that into your files, and then copy and paste that and press enter. Now you have your bed tools loaded. Let's go again, oh sorry. And then here we can just, if you wanna just see what bed tools does, type bed tools and press enter. And it's gonna give you a list of stuff that bed tools does for you. Okay, if you scroll up, you're able to see what bed tools does. These are the commands that work with bed tools: intersect, window, closest, average, coverage, map, genome coverage, merge, cluster, complement, subtract. Now we went over a few of these as part of our class. The rest of them were supposed to be your homework. So go through these commands on your own. There's also the bed tools website, which has a wonderful tutorial. I cannot emphasize that more. If you want to understand bed tools on your own, just go to this website. Just search for bed tools on Google and go to this website, and it has this tutorial, which is very comprehensive. Just click on tutorial, and then it comes. This link comes up, which talks about every single command. And actually, this is the tutorial that we went from. This tutorial that we're going through is exactly this, except this one contains images to help you understand what intersect does, which is what we went over in class. Okay? So if you want to go through the same tutorial and you want to do it here, you're welcome to do that as well. Follow this one on the website, because this has these images and stuff, so it helps you. But I have modified some of the things, so just make sure you do those modifications as you go along, especially the advanced part. Alright? So the advanced part is modified. We're not doing some of the things here. Okay, so let's go back. We open our, in our text wrangler. These are the commands that we want to work on today: intersect, merge, subtract. There are some other stuff as well, coverage, genome coverage. We'll go over them step by step. So let's start with the bed tools intersect. The intersect command is a workhorse. It's very common. It's used, it compares to bed, VCF, GFF files, or a BAM file, and one of the bed, GFF, or VCF files. Okay? Does that make sense? So either you have two bed files, GFF, VCF, or any one of these combinations, or you have one BAM file and a bed file, a VCF file.
And the intersect is one base pair.
Yes. So, what's wrong?
Yeah, no, it's just.
You're still with it?
Yeah, still with you. Yeah.
Okay.
Yeah.
All right. Stop me if I'm going too fast, or if you if you feel like this is, because the whole point of the tutorial is to make everything clear. All right.
Did we learn how to change the intersect length? Did you teach us how to do that?
Intersect length.
Yeah, like let's say if you don't want one base pair, but you want, let's say, 100 base pair. You only want regions that at least overlap with 100 or more.
Yeah, so that's a good question. I think the way to do that would be to search bed tools intersect, specify
Right.
length, Google. Yeah, I doubt if it does that.
Okay. Because I thought you mentioned that you have the option of being able to do that.
I mean, was it? So here are the options, right? So you have
okay.
A, B, ABAM, UBAM, BED, WA, original entry in A, original entry in B, left outer join, that is for each feature report the overlap, WO, WAO, I don't think this is it.
That have no overlap or.
Right. Minus U,
Minus V is minus no overlap.
right. So this is the minimum, minus F,
Minus F, okay.
right? So
As a
the-
fraction of it, so you can like put 10% or 5% or whatever.
got it? Okay. So, does that make sense?
I mean, I was just wondering, how is this possible to have one base pair overlap? I mean, do you still call it as a read?
Yeah, of course.
Well, you're
I mean-
comparing two reads with one another, so.
Actually, you're comparing two regions. You're not
two reads, not to the reference.
You're comparing two regions that are specified by your program. So these regions are basically could be a pile down of the reads. So it's like a pile up of reads, and you have defined a region. So this was something that we went over in the class. If you go over the video, you'll see that we talk about this in detail because we want to explain the confusion that there are. So this region, the start and end is what is defining this region, but this region is essentially a pile up of all the reads in that region, and we just chose the first position and the last position based on the read pile up. But once you have a region defined, you have a definitive start point and a definitive end point. So if that region overlaps by one base pair with another one, you will say that there is an intersect there, right? And the output, the way it occurs is that it goes over each region. And what he's saying is, I think, is the coverage part of it. Basically, when you explain the coverage, that's when you know how much of that intersect is there. Is it one base pair here, one base pair, one base pair, one base pair, or you have multiple. If you're doing multiple files, then you'll have multiple overlaps. Do you know what I'm saying?
Yeah. I was thinking of aligning to the reference, but.
The reference alignment has been done.
That's already
Yeah,
done.
so it is.
So these are now,
comparison within the
yeah, you're comparing two files that have been aligned to the same reference, and those alignments have given us regions. That's what you're doing. And we're now comparing the regions.
Okay.
We're no longer in the state of the alignment part. That's gone. Okay, so moving on. So let's go ahead. I mean, there's the A file cpg.bed. There's the exons.bed. Go ahead, copy, paste, and head -5. You get the 5, where minus A minus B. It gives you the intersect. Now,
Vishal?
Yes.
On the readout there, the display that you get, the CPG colon 116, do you know what that is referring to? Because we don't have a write A or write B command here.
no. So that's the default output. What do you think it is? Let's just play it the other way around.
What do I think it is?
Yeah.
So I can see that chromosome 1, but those are two locations. So assuming you have the same nomenclature in both files, chromosome 1, that's a start and an end. So,
So
chromosome 1.
Let's open these files and see what they are. Why speculate, right?
Okay.
Let's just go less. This is the first line in this file,
Okay.
right?
I see.
So this has, remember the coordinates, 28735, 29810.
Yeah.
Okay? So now, right? So 28735,
So I guess it doesn't exist there, so it's closer enough.
no wait,
I see.
29320
Yeah.
is the starting point, which is here,
Yeah, so that's the first intersecting
location.
region.
And then it goes till 29370. So that entire second, the first CPG region overlaps this entirely. But notice the start and end are this start and end, not the start and end of the CPG.
That was a longer region, right? In the
Yes.
CPG?
So it's a longer CPG, but it overlaps a shorter region, so we have the start and end defined. So what it's outputting by default is this. Your start and end from the previous exon file, and it's saying that CPG 116 is your overlapping unit, because that's what you want to find out. You want to find out the overlaps of A in file B. That's what you're looking for. Okay?
So that's the name of that
Right.
sequence.
So let's do an experiment,
That's
all right?
yeah.
Let's do something different. So how about we make this A? Did anybody try that?
No.
Okay, so let's try this. Let's make this A and that B. What happens now? See? You have the same coordinates, but the name has changed. And this is now saying that because we're interested now which exons overlap the CPGs,
Yeah.
not which CPGs overlap the exons.
Huh.
I see. So it goes to the name of
That's
that.
cool, that's all you have to do.
Right? Yeah. Just change the A and the B, and then you're basically saying I'm interested in A, not in B, but I want to find the overlaps of A on B. So give me just the information for A. But the coordinates are from the B because that's where the overlap is. Does that make sense?
So then the default is basically right B.
Default is right A.
Right, yeah.
Is it right A?
Yeah,
here
because
you're- oh,
this
yeah,
is
yeah,
A.
you're right, yeah, I'm sorry, you're right. Default is right A, okay, got it.
Okay. Okay, so moving on. So bet tools intersect with this WA WB. Now WA WB becomes clear, right? So once you found the overlaps, then you know you take the list of overlaps, and then you can just look at other stuff for that. Like,
Yeah.
And then Roger.
or if let's say you want to be like, okay, now I have these overlap regions, but now I want to find out what's the nearest promoter. So you can use that to find for these, or you can be like, I want to find out if there are any other whatever non-coding regions, annotated non-coding regions that overlap this. Yeah. You can just download a bet file of the non-coding regions. The repeat master has the repeats. You find out the same exact command. Intersect gives you whatever of these CPGs intersect with the non-coding regions. So that's why we're teaching. That's why we're learning these things. Like we're trying to figure out what are the most important tools. So this is one of the most important tools that you'll be using, because you'll be going from here on. Whenever you want to find out anything related to something else in terms of distance, this is where you come. So anything related to distance, is it how close, how far, because you have regions now. When you have regions, you can find out, and everything on the genome is a region, right? You define the exons are regions, genes are regions, CPG islands are regions, promoters are regions, ChIP-seq peaks are region, So all of these regions is what you are interested in, essentially saying that, okay, yeah, where do they lie? How do they intersect? What is the difference? Can I merge them? Like if you have peaks from ChIP-seq and you have two different files, and you want to basically create one merged peak file from all these ranges, then you just use the merge command and you have one file with all the merged peaks. Okay? All right. So then counting the number of so again intersect minus C gives you a count of the overlaps. So like you have this CPG, but it also tells you how many regions are there that are overlapping. So you have one region that overlaps this in this case. Here you have 3 regions that are overlapping within that one thing. Alright? It's not the count of the base pairs. It's the number of regions that are overlapping. Okay? Does that make sense? Everybody?
Say it one more time.
So it's not the number of base pairs overlap. It's actually how many regions are there that are overlapping this region, the first region. How many regions in A are overlapping with B? Okay? Does that make sense? Because in a bigger range, right? Supposing you have bigger range and then you have multiple CPG islands within that range. You see the second file, or you have multiple exons. Say you have 3 exons and then you have one CPG region. So these 3 exons overlap in one CPG region, which is why this number is 3. And here you only have one exon that overlaps the CPG region. That's it. That's what you're getting. How many exons overlap the CPG? That's the answer.
Yep.
Okay? Okay. Then we go to minus V command. So this is just the make sure there's a pipe. There's a typo in the file there, so just make sure there's a pipe head there. Okay? So then you get the regions that do not overlap. Okay, this is just a complement of the first command. Make sense? We're good? Okay. Alright, let's pull through the simple stuff. Because we gotta have some. So alright, so WO command is demonstrated here with minus F of 50, 50. 50 being the 0.5, which Mo was talking about, the percentage of overlap. Minus F, and WO. Basically, recall the default is the report overlaps between features A and B so long as one base pair overlaps, and then however minus S allows a bigger fraction. And then let's say 50% of the overlap gives you this option. So WO gives both A and B's information, and then it also gives you the ones that have at least 50% overlap. Alright? Does that make sense?
What is that number at the end? 439.
That's a good question. Uh, it's not part of this, right? Let's okay, so let's see. Let's just search for this. Okay, so it's not part of this.
It's like the number of base pairs
Yeah.
in the interval.
Right.
If you
Yeah.
subtract,
Oh, I see.
it seems to be this, but then, oh, they're all, yeah, no, they're not all four.
There's 348, 439. So notice,
But a lot of them have the exact same number. Maybe
Yeah.
It's not a coincidence,
Yeah.
Huh.
but it does seem to be the subtraction.
I also get a plus or minus on there.
that's the strand.
That's just the strand.
Let's see, first of all, so does anybody know what WO is? So maybe that's the tool that we want to see. So you go there, let's see, bit tool, intersect. Okay, so WO, right, so original entries be plus the number of base pairs of overlap between
Yeah.
the two features.
Yeah, that's right.
That's the number that you're seeing. Okay? So if you go back and calculate, you'll find that they are actually the same number. Okay? So only A features with overlap are reported. Got it?
Yep.
Okay, perfect. So when in doubt, Google. Alright, merge. So basically it's a way to merge, as the name suggests, you have a sorted by coordinate file. So you make sure your file is sorted and then you just submit merge and then you get your merge file. So right now it's just gonna keep going because we didn't go more. You can pipe it to more. So you get your the intervals are merged, whatever overlapping intervals were there in the file, they are merged into one interval. Does that make sense? 2 units overlapping each other, they become 1 unit. That's all that's happening. 2 units, 1 unit here, 1 unit here. Remove that, you have 1 interval. That's it.
That's only for one file though.
Yes, we're merging the intervals in one file.
Yeah, so,
I mean, a simple way, if you have 2 files, just cat one next to the other. That's what you do. Here, you just go cat file 1, file 2 into file 3. Okay? Do you know what happened here in this command? You appended 2 files and created file 3. Okay? Does that make sense? And then you just go bet tools, merge, whatever, file 3. That's it. Does that make sense? So that's a simple way to create a merge file. Okay. So here is an example just saying that it should be sorted. If it's not sorted, then you'll get an error. Alright? So in that workflow which I just mentioned, you would have basically cat file 1, file 2, then you go sort minus k, 1 1 minus k 2 2, file 3 dot bed to file 3 dot sorted dot bed, and then you do a merge minus I, file 3 dot sort dot bed.
Can you go like what is K here, K1, K2?
Anybody want to answer that? Anyone who attended the lecture last time and was paying attention?
that's the same question.
Take a guess. Anybody?
I think it's the coordinates, isn't it?
Yes.
The coordinates, the genomic coordinates.
Yes, the genomic coordinates are columns of your bed file. So here you're interested in this and this. So that's why it's 0, 1, 2. So 1 and 2. Okay? So you're saying this sorted based on this and then this. So supposing you have another column here, let's say, assume that there was another column, then this will be 2, 2 and 3, 3. And n is saying that they are numeric.
Oh, and it's just numeric.
I guess I was trying to, why do they, why are there two, why is it one, why not just one? There's something
Because you can, I
different
think the
between
one
column.
means that use that as your first sorting
okay,
option,
okay,
and then
gotcha.
the 2 that comes after the
see.
second one, use that as a second.
I see,
And then the
So
first
you
column.
could switch to K1, comma 2, and then K2, comma 1, right? And it was sorted based on column 2.
Yes.
I think that's what that means.
okay.
Well, it's a good thing we can Google this, or or we could just go man sort, and then go to minus k. Key position 1, comma position 2. Start at position 1, origin 1.
Yeah.
End it at position 2, default end of line. So where is the origin? In position 1. So maybe my understanding then is that it starts at this position 1, but you want to start it based on the origin first thing here, not here. So you want to sort it by in the coordinate system where the largest value, place value, is this position, and that this is not the largest place value. Does that make sense? In that number. Got it? Supposing you had a different system where, let's say it's reversed, then this would be 3, 7, 8, 1, 1, then you can actually give preference to this one as the starting position where it's got the most value. Try it, see if it works and brings you a different sorting than this other one. Right? Let's try it. So let's see. Okay. So this was our command, right? Let's just do. Okay. So now first we do this one and then just see. Actually, I could have just done a less on the other one. Okay. So you have 11873 1227 like this, right? Yeah, we have that. So now let's sort it and then just name it 1, 5 and 2, 5. Okay? This is 5, right? 1, 2, 3, 4, 5. Right? Although it'll be different based on, like, here you have, for the first purpose it should work. Alright, so let's do that. Sorting. Look. So it's changed. The sorting order based on the fifth position.
So this is the real coordinate. That was the last 5.
So see, notice the fifth position here is 0. So
Yeah,
let's
yeah,
put
yeah.
all the zeros here. And then the ones come. The ones and then the 2s. So it's sorted by this position now. 4, 5. Are you seeing this? Isn't that
That's
cool?
an amazing level of
Isn't it
control
cool?
you have. That's
See the
Unix.
level of
That's
precision you
power.
have in Unix? You can specify the exact digit by which you want to sort.
Really amazing.
It's cool, right? Alright. I think it's cool. Okay.
So if you kept the name Exxon sort.bet, it would override that one,
Yeah.
right? It would just write over it and then.
Yeah, new file would be created. Alright? That's why we do 2, 2. I learned something today. It's awesome. So bet tools merge. Basically, once you have the sorted file, it merges it. Just copy paste that statement. You'll have your merged file. So now the next step is to count the number of overlapping intervals. A more sophisticated approach would not only be to merge overlapping, but also report the number of intervals that are into the new merged interval. One does this with -n option, meaning that you want to find out how many intervals were merged. Just like in the intersect, you want to know how many portions were overlapping. Here you want to know how many intervals. So most of them are 1, but here you have 2 merged intervals. Like here you have going down, you have 2 here. Anyways, right? Simple stuff. Merge -i this minus d 1000. So minus d option one can also merge intervals that are close to one another, but do not overlap with one another. Let me just text wrap this.
So 1000 is the distance between
Exactly.
two regions, so it's like 1 KB or something.
Right, as long as they're 1 KB within that 1 KB window, just count them as one, merge them into one interval. Right? So you do that when you have promoters or some other, peaks, and they're like, well, they're too close, they're within the histone range distance of the whatever 100 base pairs or 200 base pairs. I would rather count them as one peak as opposed to two peaks, because they'll be reported separately in ChIP-seq, because of the biology, because of the histone. And so they're like, oh no, these are definitely, the length is 200, they're within 200, so we'll just merge them. Okay?
And then that number there, it says how many of those regions were overlapped to create this one giant overlap.
Exactly. Alright, so next, we often want to know which intervals of the genome are not covered, so that's why you have the complement. Use the complement portion to see which ones are not exonic. So for example, here you have exons bed file, and then you have the genome file, and you want to know which are the non-exonic regions. Right, so basically, what are the regions that between 1 minus the input file are actually the complement of those? Got it? So like say if this is the genome and then this is the region of my interest or the exon, I want to know everything here and here. That's it. Okay, the BedTools genome coverage. For many analysis, one wants to measure the genome-wide coverage of a feature file. For example, we often want to know what fraction of the genome is covered by one feature, 2 features, 3 features, etc. This is frequently crucial when assessing the uniformity of coverage of the whole genome sequences. This is done by the genome coverage tool. As an example, let's produce a histogram of coverage. For exons throughout the genome, like the merge tool. Genome cover requires pre-sorted data. It also needs a genome file. Okay, so you do a genome coverage minus I to minus G, and then at the end your output will show something like this, like genome 0, this, and then 0.9, like a fraction that, So you can use this to produce the bed graph option with the minus BG. So you can view it in the genome browser as a bed graph file. We haven't really done that, but you're welcome to open this file as a genome bed graph file, and then it gives you these region with their coverage of that.
Michelle, just a note, you might want to add the head thing to the top one.
Because it runs forever.
Yeah. I just did that.
Okay, sorry.
That's okay.
Yeah.
Could you go over the numbers that you get in your output, what they mean? In that, when you run that?
This thing.
Yeah, the genome coverage.
Okay.
This one here. It says it runs for 3 minutes or more. It's at 263.
So if you ran it, what do you think these numbers mean? You ran it, right?
Yeah, it keeps running. How do you? I typed in quit. It doesn't work.
You should type head first when you run it. So
Yeah,
Control
no,
C.
it's too late now.
Control
It's
C.
too late.
Control C. Control C.
Control C.
Oh, that's nice.
That should stop it.
Yeah. So let's see what.
So if you ever are in doubt like what the numbers mean, you go back to BedTools and then you just search genome coverage. So this is right here. And then you have, these numbers minus, first of all, you want to see what minus I is, right? Minus I is probably the input file. Does that make sense? Minus I is the BAM file and minus G is your genome file, alright? So this is the default option. So by default, it computes the histogram per base pair reports, and so per base pair reports is minus D, and minus BG summarizes the feature coverage. But by default, it just gives you the basically how many per base pair, what is the coverage that you have. Now how did it get 0.9 here? Genome cover minus I genome.txt. Alright, so let's go over this. So first thing you want to do is see what your sort bed file looks like. This looks like this. These are integer values. Let's just say we remember this part. And then let's genome.txt. So
Oh, it tells you the size of each chromosome, that one. And then I think it reports the fraction of the,
right,
it just divides the two numbers together, okay. I
yeah,
think that's what it is.
yep.
Yeah. Might do a per chromosome.
Just to
per
show.
genome.
Just
But
presents the top.
it's just calculation goes for values. Yeah. Exons are about that, and that's your exons and much. 0.9 is only 1% of the genome, or 1% of whatever. Big.
So this 0.9% of the genome is
I think in
this.
the website it kind of shows, I saw lower down, I don't know if you went low enough, but if you go farther down, I saw a little artwork on the genome coverage. Yeah, there. It seems to go through.
This one?
That's not the same output.
Oh.
It should, I thought it was.
Actually, we could go here. No, the actual binding site. Hold on. So if we go to the tutorial part of Betul, the one that we have here. So if you go on the website here, we are in genome coverage here. But even this doesn't explain much.
No.
I mean, obviously it's some fraction between this and the other file. So when you say genome 0, and how long is this file? Like if you let it run, it's giving you all the way.
I didn't let it run all the way to the end,
Okay.
but I think maybe.
So I think this first tells you the region that it overlaps, right? The coverage of that region from the file, exons.bed. So you have an input file, exons.bed, right? And then you're trying to say basically what portion covers this with the genome. But then normally this should be a whole number. And here it's saying 0.9, right?
I think that's a fraction, right? So it's
Yeah.
like 1%. So
Yeah, it's probably.
I'm just not sure when it says 1%, what it's reporting. Is it reporting
The 1% of the genome or 1% of the.
No, I think it's 1% of the genome. So I think it's your feature, whatever that is, divided by the genome.
Genome, yeah.
But I don't know what genome 1, genome 2, genome 3, what those are.
I think they're just the features from your exon file that overlap with the genome.
Oh, I see. Maybe that's what it is. It gives you the coordinates of the feature and tells you what percentage of genome that is
Yeah.
when you've merged everything together.
Yeah.
Maybe that's it. Okay. And then it lists the biggest one, the highest, and then the lowest one, lowest.
Yeah.
That's the way it looks like to me.
Right. So that's why it's sorted by 0.9% and then it keeps going
All the
down.
way down, yeah.
Right?
So it takes every merged file and then calculates its coverage over the entire genome.
Yeah.
I think maybe that's what it is.
Yeah. So normally, I mean, I haven't used it in this context. Most of the times I use genome coverage is in the second context to produce a bed graph output between this and the other. So this is the context in which I use it, the second one, where you have the genome coverage, bed file minus G minus BG, because then it gives you the output as this format, which is what you need in terms of, displaying it, or in terms of how many overlaps are there in that file with the genome. What is the coverage from 361 to 14409? There's 2. The coverage is 2. So they're covered by how many of these regions cover that particular region in the genome. Okay? Still with me? So yeah, then it talks about principal component analysis, which we don't go through on this. That's why I was saying that, you know, if you want to, you can go through this on your own. I mean, it's interesting. There's some R involved, but they give you the code and everything, so you could technically go through it if you wanted to after you learn a little bit of R. In the meantime, let's continue. We're kind of running out of time already. So, bed tools, I think we're almost there. So genome coverage minus I minus BG, this is a step where you get the coverage for each region in the genome for this file and how many times it covers the genome. Okay? It's like you have two exons that cover this region. Okay? Alright. And then now we get to the advanced usage where we want to mask all regions in the genome except for the targeted capture regions. So step 1, we add 500 base pairs upstream of each probe. So let's first look at our probes file, which is our input file. Right? So this is our... Oh. So maybe that's why you got an error. Wait, what happened to the probes file?
It's not there.
Somebody remove it? Hold on. Does that mean I have to download the whole thing? Huh?
I didn't actually try to run that command because I saw the final output was already there.
Yeah,
So, but I don't know if we need the probes file or anything else.
exactly.
We could subtract 500 maybe.
Huh? Yeah, we could subtract. That would be a good exercise. Create a new file by subtracting 500 base pairs. It's gonna take forever. Alright, well, let's try and do that way then. We can, you know, add 500 base pairs by doing minus B. So let's just first look at slop. Alright, let's start at the very beginning. Let's go look, or simpler option is obviously we can just download this BedTools file again and we'll be good. The other thing we can do is just look at, alright, so we can look at slop. So slop will increase the size of each feature in the feature file by user-defined number of bases, while something like this can be done with awk. BedTools slop would restrict the resizing to the size of the chromosome. That is, yeah, you can't have less than 0 greater than chromosome size. So that's why you have the genome file with there, because it needs the genome file to tell you whether you want to, you don't want to go over the chromosome size limit. So because when you're adding base pairs, right, so that's why. So increase the file by the same number of base pairs. Is there a way to decrease it? Wow, there's no way to decrease. However, if requested, the number of base exceeds the boundaries, it'll flip, resizing according to strand, increasing the size of feature based on strand. So it's all increased. So what if you want to decrease? See, why don't everybody try and see if they can find something that helps reduce the size? Just go Google and see if you can find something to reduce the interval size. So there's slop comes up again and again, but that's just to increase it. What if we, oh wait, is it minus L?
Yes.
Subtract, minus L, yeah, it's right there. It was right after minus B.
Oh, yeah. Subtract myself.
Okay. Oops. So let's do that then. So what will be the command? BedTools slop minus what?
L.
And what's the number?
500.
What's the file?
Probes.500bp.
What's the output?
Just whatever name you want to give it.
Probes not bad. Yeah.
Ooh, error.
This file, something will get replaced.
Yeah, it'll be, so yeah, go ahead, run it if you want. I mean, it's not gonna, it's just gonna rewrite that whole thing. That's
Okay.
okay.
I was thinking about it. The next one too has a hg.fa file.
Yeah, so if wherever, oh, there's a faster file.
This one we have the hg.procomplement.mass.fa.
Yeah.
Maybe there is a file that's a file.
Okay, so I think all of this advanced stuff is for, just using the HG19 genome. If you want, we can, I'm pretty sure we have it on the server.
I don't really feel
Huh?
I'm happy to move to the next thing if,
Okay.
if that's.
Well, I mean, we have it on the server, I'll just have to look for it.
I like the HTC thing.
Yeah, that's actually more important.
So when do you want us to start in our term project or whatever?
Now, you have enough background to start.
Really?
Yeah, I mean, you know how to align, you know how to, get the counts. Just finish the alignments at least.
Yeah. So we start with the FASTQ file, right?
Yeah.
You want us to start with the FASTQ file
Yeah.
just off the machine and then take it
Yeah.
all the way through.
Yeah, 2 alignments.
Okay. But when is it due?
Well, it's due.
We all need deadlines.
It's due in May. Let's make it May 15th. Right? A month from now?
That's a Sunday, man.
Wow, you're good. It's May 16th then. Right, it's due Sunday night. That's right. I was right the first time. Spend your weekend doing that. Okay. I think then the other thing is snips.calls.bed. Do we have that one? Snips.calls.bed? We don't. Let's skip the the advanced stuff for now, because essentially it's just going over the same things, except it's using the real files. So maybe these are just more of examples that you can go and try to download. So like if you have the HG18 FASTA file, you can download these files. Let's say HG18 FASTA, I would go to UCSC Genome Browser, and then, or just here, type hg18.fa. And then you can come over here, index of golden path hg18.fasta, you can download it from here. This is the entire genome. There you go. Sequence annotation download, you can go to human, and then you can download the full AG38. There are other 37, GRCH, HG18 full data set. So you can download this data set by HG18.2bit. This is the file that you will download, and then you can use a utility 2bit.fasta to convert that from 2-bit to FASTA. Okay? This is the file. So 2-bit files are essentially, and the way to download is very simple. You right click on this and copy link address. Okay? Then you go here in your directory where you want to be. For example, let's say in my case we usually download our stuff under we have a special directory that we have just for genomes. Alright, so data pub genomes. And here we have all the genomes that we're interested in stored here. So GRCH38, 37, mouse, HG19 is here. We don't have HG18 because we never needed it. But if I wanted to, I would create a directory mkdir HG18. Okay? And then I would go to HG18 and then do a wget command with this link. which I just copied. Okay, if you do a wget, and it's gonna start downloading. It'll take another 15-20 minutes. So I'm gonna cancel this download because I don't want to wait 15 minutes for you to just stare at me. So we're gonna cancel this. But this is how you do it, all right, to get a new genome. So that made sense? I followed 3 or 4 steps, went to the UCSC genome browser, went to their page where you download the full sequence annotations, go to whichever genome you're interested in, like human full data set, click on the full data set if you want HE38. You know, go to the 2-bit file. Oh, here they have actually got their entire FASTA file. So you just download this file. You don't need a 2-bit here because they have the FASTA, although they have the 2-bit as well. So 2-bit format is like a compressed version of the entire thing. So like this should technically 797 MB, whereas this is 938. Okay, so it just saves you more space. Okay, and then you know how to unzip, right? GZ, you just go tar minus ZXF or ZXVF, and it'll make this from GZ to FASTA FA. Okay?
So you wouldn't use gunzip, you'd use the tar.
You can use gunzip too.
Gunzip too.
Tar, if it's TGZ file, then it's tar.
Yeah,
If it's GZ, then you do gunzip. Okay, or gzip. Okay? Got it?
Yeah, and the link, how to
So if you see here, there's a 2-bit file, right? So to convert it to FASTA, you have this utility called 2-bit to FASTA.
No way, really?
Yeah. Hold on. So there's this 2-bit to FASTA. So you download this thing called UCFA to 2-bit and then 2-bit to FASTA. So the way you do it is this one, 2-bit to FASTA utilities. And then the way you do it is you go module, load, UCSC tools. Okay? So this is, I'm just telling you this, we didn't cover it in class because it never came up, but it's good you learned this in practical. So module load UCSC tools is these UCSC tools which we need. Huh. I thought we had UCSC tools. If you don't have access to it, you may want to contact the HPC and they'll give you access to UCSC tools. For some reason, it's telling me it's not there. Okay, let's see if this works. It worked.
Oh, so it's not called UCSC tool.
It's called module load UCSC.
UCSC.
Okay, so just module load that, and notice that it gives you 2-bit to FA input.2bit, output.FASTA. That's a simple command. Input tbit file, 2-bit file, output FASTA file. Got it? Right, so this is where you will go 2-bit to FASTA. Your input file is hg18.2bit, and output file, let's just call it hg18.fa. And it's gonna start, it's gonna say end of reading file this much, and then this file is 0 bits because obviously our file is not complete yet, so it's not gonna be able to run it if the file is incomplete. Right, so it's saying end of file reading these many bytes. It needs both. Yeah. Yeah. Okay. Alright, we need to download the full thing and then it should work. Does that make sense? Everybody on board? So you can download these files if you want for yourself and then just, run these advanced steps. Essentially you just need the hg18.fa, the FASTA file, and all of these should work. You might then here it's just doing the intersect between snip calls. You can download a snip calls file that from the UCSC genome browser and run this on your own. Alright. Let's move on to the interesting part here, the htseek part. So module load SAM tools, and then you have the accepted hits.bam file. You index that. Alright. So So just stay in the Bet Tools demo, and here you have your accepted hits.bam file, right? So when you go module load SAM tools dash 0.1.18, I've done this too many times. So, okay, so this is your SAM tools, module load SAM tools 0.1.18, right? That's the one I use. Then you go SAM tools index accepted hits.bam. Okay, we're just creating an index file, right? So ls, you should have a bam.bai. We do. Okay, new file was just created. All right, everybody with me?
How do you do the
I'm
command?
a little behind. I just
Okay.
loaded module load samples. What did
And
you
then SAM tools index accepted hits.bam. We're just creating an
That's
index
if
for the file.
Everyone already has that file.
We have that file now.
So don't do anything bad.
You don't need to do it, we have it. If you do ls, you have this file right here. I just created it. Okay? That's what happened when I do the practical. I'll create files for you. Okay, so then the next thing we want to do is just create the chromosome 20 file. We don't technically need to do it for htseek to run. It's just an example of how you can extract only the reads on chromosome 20. Does that make sense? Everybody with me? If you're interested in just working on one chromosome, this is what you do. You don't need to do it.
Yeah.
Okay? So we're gonna Control C, Control V, you get the SAM file. If you do an ls, you have the where'd it go? There you go. Accepted hits 20.sam. And then same way like we did for SAM tools index, we're just gonna create an index for this and create a BAM file. Actually, we're gonna create a reads.bam by this. Alright? Essentially, we're converting accepted hits.20.sam to reads.bam. And you'll realize why we did that in a second. We did that because we wanted to run BAM tools BAM to bed, and we wanted to run that on this, so we don't want to have too much memory used. That's why we did this and converted it into reads.bam here. Does that make sense? Are you still with me, or have I lost you?
So, no, I think
So we're trying to find the coverage of this file.
okay.
Okay,
In
so
order
this
for us
dash
to get the coverage, we have to have what kind of a file?
BAM.
BAM files. Okay.
Okay, and so well, actually we need to have a bed file in this case, but I wanted to show you how you do it directly from a BAM file.
Okay.
All right.
Sam's BAM, and then now we're using the BAM to do the coverage.
Got it? Okay. So we run this, and boom, it's running. And the reason why exactly this was the reason, because it runs almost instantly, is why we create only chromosome 20, just as an example. That's why it's fast. Okay? The next step is to require coverage to be from properly paired end reads. I'm going to skip this, you can run it on your own if you like. And then this is computing separately for each strand. Again, this is just grabbing the plus strand here, so you're only getting the coverage for the plus strand. Feel free to try this on your own. This should work because once you've done this step, you have the proper coverage, and then this is the forward coverage from the genes.bed and the reads.bam. Do we have a genes.bed file? We have an exons.bed. Do we have a genes.bed file? No, right? So if we don't have a genes.bed file, this won't run. You can just run it till the exons.bed, till here, right? Here, literally the only thing you're doing is grepping the ones which have a positive. And this slash, backslash, and dollar means just grep the plus sign, which should be on its own. It's not combined with any other string. Do you see what I'm saying?
That's what the dollar sign stands for?
That it means, yeah, it starts at plus and ends at there. So don't look for anything like, don't look for ABC plus or BC plus plus, or don't look for BC plus ABC. Don't look for these strings. Only look for the dollar sign. And so you're grepping that, and then you're feeding that to the with your genes.bed, saying, you know, this is my input for the plus strand only. You see there are 3 pipes here. First thing, you're converting this BAM to bed, so you're getting a bed file from your BAM file. Then you're grepping only the plus strand ones here. Then you're passing that as input as A. Notice this dash here? This is going to be replaced by this input right here. Okay? So then you're saying that, okay, this is my A file, B file is my genes.bed file. Okay? If you really want to run this, which I'm guessing some of you might, we're just going to go to UCSC Genome Browser or Table Browser and download a genes.bed file. Alright? Does that sound good?
Mm-hmm.
Did everybody like that? Okay. So we go to the table browser. So which assembly are we using here? Is it HG18 or 19? So this was aligned to HG38. Okay, so this is where it gets confusing, right? So this data set is different. The alignment file is created on an HG38 alignment. Okay, so if you want to use this BAM file, the reads.bam which we created, which is from HG38, we're not going to use HG18 as specified here. Where did we use HG18? Over here, right? Somewhere in the top. Okay, that was separate. So this is good. So this was for the probes file. This was separate. This is separate in bed tools here. So what we're going to do here for our genes.bed, we're going to download the HG38 genes because the accepted hits.bam or reads.bam that we've created is on that genome. And those have to match. If they don't match, then we're not going to have the right output. So the way to do it then is to go here, select the HG38 assembly right here in the top. You see it? On UCSC Genome Browser, you select HG38 and then human, go to genes and genes predictions. We can just select the refseq genes. There are multiple options. You can look at the ones that work for you. For the purpose of this, we're just going to look at the refseq genes. Okay? And then here we can go in the ref flat format. And I'll just show you in a second what it looks like. So if you just do get output without the blank file, it looks like this. This is your, wait, we wanted a bed file, right? So we go back, and select the output format. So here you can select in this field the output format. We're going to look at the bed format here. Is everybody able to see this?
Yes.
Okay, so we select the bed format. Then we create the get output. And so it asks you whether you want the whole gene. Let's just say whole gene for now. So you get this as your bed format file. So you have the chromosome 1, this is the file name, gene name, and these are all your genes, right? This is going to be exactly what our files look like. We are interested in the first 3 or 4 columns of this, but there's other information as well, which, you know, as long as it's in the bed format, we're okay with. So this is important stuff. I just showed you how to download a genes.bed file for yourself in future if you want to get all your genes in the bed format. Okay? You go to UCSC Genome Browser. Sorry, here. So today we've learned first how to download your entire genome FASTA file from UCSC. We've also learned now how to download individual tracks from the table browser. Are you with me? I hope you're with me. Okay, so you go here to the table browser. The way to get to the table browser is to go to the UCSC Genome Browser and under Tools, it says Table Browser. You go there to the table browser, which will bring you to this page. Then you select your mammal or a vertebrate, whatever you're using, species. Then you go to human, mouse, whichever organism you're using. So we're using the human. We select the assembly. We're using HG38. We also have HG90. They're just different versions. Notice they're with date. So this came out on December 2013. This came out in 2009. The next one will be coming out in 2000 whatever. But then we can use that. Now we select the group we're interested in. Are we interested in mRNA? Right now, no. We're interested in genes. But it's always a good idea to look and see what is included in mRNA. So it includes human mRNAs. If you select that track and you select all the human mRNAs, these are your options. You have the MCG genes. I don't know what those are, but they're there. Alright? I'm just saying that's an option. You have RefSeq genes here as well. So that's another way to get here. If you're just interested in the mRNAs and the express sequence tags, as opposed to all the genes. So if you're interested in all the genes and gene predictions, then you go here. Okay? Does that make sense? Okay.
The whole genome is which one from here? If you wanted the whole FASTA.
The whole FASTA is separate. So
You
whole
can't-
FASTA is just go to this link. You just search for, go to UCSC Genome and then you go to genomes instead of tables or anything.
Got it. Got it.
Right? You can go here or you can just go download using HTTP. Download sequence and annotation. So using HTTP, you go here and then you go to the full data set on whichever version you're interested in. Okay? HG19 and then go to the full data set link. And then over here you have your files. And so here you have your 2-bit file, HG19.2-bit. You download that if you don't have the fasta.gz, in which case, in this case you don't. So you just download the 2-bit file. Notice on this page you also have other stuff. If you're just interested in express sequence tags or ESTs, you can download those as well from the fasta.gz format. Okay? This sometimes you need the chromosome sizes file. So this is just a file that contains the size of each chromosome. Alright? So all of this is there on UCSC Genome Browser. You just have to, play around and get it, but these are your useful links sort of to say. I use the table browser to download the stuff that I need because they're in a particular format. So sometimes I want BET files, sometimes I want other files. So notice in this case, okay, human this, I can also just do known genes here from GenCode. Instead of going RefSeq genes, I can go to known genes, or I can go to LinkRNA-seq and get just the LinkRNAs here. Does that make sense? I mean, there's lots of information, but you gotta know, like if I want SNO and microRNAs, I just select the SNO and microRNAs here. Okay? But anyways, right now, let's just do GenCode and known genes.
If I'm interested in link RNAs, like whether it will tell me the source, everything is from embryonic stem cells or like.
So you have to open it and see what it tells you. I personally, I don't remember. So if I was to do LinkRNA, RNA-seq, just open it and see what comes up. Like, select this and so it says which ones. Adipose,
there
brain,
you go.
breast.
That's great.
Which ones are you interested in? Colon, heart?
Yeah.
It gives you all these options. Right? So right now, let's go back to what we're doing. Genes. GenCode, genes.bed. We're running out of time. We have to finish. Okay. So known genes, let's go there. Let's go look at the format. The next thing is the format. So you can get it in GTF format. That's one way to download it. The other one, which I'm telling you now, what we need is the BET format. Now if you don't enter the output file, it's just going to say simple BET format. And you get output, it'll display it on the browser itself. So notice I click get output and it's on the browser. Oh, it asks you whether you want upstream. So this is very useful. Sometimes you want BET file for something which is upstream by a certain amount of regions. So instead of using BET tools to calculate the range, you can just do it here. Okay? Just get the BET file, and this is our BET file. Except this is now in this UCSC format, which is weird, and I don't understand this sometimes. So then you go back, you can do RefSeq, and then you do that format for known genes, RefSeq genes, which gives you the ID, sequence ID. Alright? Alright, enough on that. So I'm gonna skip this part then, because now what you can do is just download this genes.bed. It'll download to your local machine. Then you FTP it using CyberDuck onto the BET tools folder on the server. And then you run this command and it shall work. Does that make sense? Everybody on board? Somewhat? Do you want me to do it and show you? Or you want to try it yourself if you want to do it? Just try it yourself. It's not too much. Go to UCSC, go here, select this RefSeq genes, select genes and gene prediction, select RefGene or known gene ID if there is. select the ref flat format. Alright, and then I'm just gonna say ref gene dot bed. Alright, and then just get output. Now get bed is just gonna give me the output of the whole bed file. And it's gonna store it on my computer, which is running out of memory.
How
So
does it know where to put it? Does it just put it in your?
it's just gonna download it and start putting it in your download folder.
Okay, gotcha.
Okay, I'm gonna pause this again. It's a huge file. It'll take a while to download. So anyway, so download this. Once you have this file on your thing, just open CyberDuck. Everybody knows CyberDuck by now, right? You open CyberDuck and then move it to the server, and then move it to this directory, and then your command, this particular command right here, will work because now you have genes.bed. Okay?
Since we're all hyperlinked into that folder, should just one person do it in the end, or?
Yeah. So before you do all this, just go ls. And if genes.bed exists, don't do it. I mean, somebody else did it for you. Okay, let's just assign. How about you, Sue? Would you like to do this?
Just putting a demo folder?
No, just, in the bed tools demo folder, genes.bed, download from UCSC and then just upload it there.
Okay.
Yeah?
I'm gonna try that.
Okay. So she'll do it, everybody else can just, wait for her to finish that. And then now the last step, which is the HTC count. So this is the important stuff. We've covered everything else. This is the part that I really wanted to go over. So module load htseek. Press tab. See if you are able to load the htseek module. Which ones do you have? You have the 0.6.1?
Yes.
Everybody has that?
Just a slash came up for me.
Yeah.
If you push it again, it might give you the push tab again.
Yes.
Okay, just try htseek / 0.6.1. Like this, the way I've typed here.
Uh-oh.
So even if you missed everything else, just if you try this is the important part for today's practical.
Yeah, I got an error.
I got an error.
It's weird. It says it's there, but it
It isn't?
gives me an error. It says
Yeah, it gives me an error
depends
too.
on one of the modules, Python. Oh, we need Python.
So remember, last time we got this error as well. So we get this error because it needs
Python.
exactly. So what do?
The module of Python.
There you go.
We're doing 2.7.3.
There you go.
You're such good students.
There you go. Now, some of you may still get an error.
Yeah.
That would say numpy. Is that what it said? TCL command failed? What error do you get now?
I never know.
You don't get any
It
numpy
worked
errors?
for me.
Huh?
It worked for me. This
Okay, great. Great. So here, module load Python and then module load htseek. Okay? Is everybody on board?
Yep.
Right, so the next thing we want to do is we want to do this htseek count, and we're going to copy this exactly, and then we're going to fill out the details. So this command I've copied directly. Of course it's not going to work like this format. So, oops, sorry. So what we're going to do is, first of all, excuse me, write an output file. So let's just say it's count.txt is our output file. Okay? Now path to the GTF file. So do we have a path to the GTF file? Do we remember if there was a GTF file there somewhere? Did we create a GTF file? Is there a GTF file? I think we did that for the... Does anybody remember how you did the alignments? Do you remember?
Let's see.
Kinda. Let's go back to my notes.
Alright. Well anyway, so let's make it easier for you. You have this file called tophg38.gtf in the htseek practical folder. So So this particular file has the GTF for human genome 38, and that's what we need, and it's a GTF file.
RAM file from our RNA-seq.
Right.
Download some, let's say, mouse or human genome that we like. You can. What format would you generally use?
Yeah.
Like would you just use ref-seq genes? That's fine for that kind
Yeah, you can use ref-seq genes, you can use, whatever GTF format you like. You can use, most people like the known gene ref-seq, known gene format, or ref-flat, those are fine. Ensemble genes, I use ensemble gene GTF as well, so if you go to the site for ensemble genome, okay. So it's probably the GTF file that that has an issue, because both these should not have the same problem. Alright? So let's try something else. There's the other
But it says that the error is in the BAM file though.
yeah, which I find is a little weird. Because here.
Oh,
Let's see. Okay, so I'm just gonna use a different GTF just for the purpose of this and see if that works. This is a bigger GTF, so there's a chance that this was a GTF. I highly doubt that this would be because of the BAM file.
Hey Vishal,
Yeah.
I gotta run, but this is definitely something I wanted to learn from this class. Is there a way to
So
get a kind of cleaned up instructions at the end of how I can practice this?
yeah, basically, if you first go online and download the GTF, and then you have your BAM file, and then you just run this command, the one that we're running, htseq count minus m intersection strict, which is a part of your minus s no, which means stranded is no, and then after that space, the first line, the first file is your BAM file, and then the space, second file is your GTF file, and then the output is to counts.txt. That's it. So the other option for you is to go online and just Google htseq count. htseq count. And then this also gives you a tutorial about how you want to do. So try it out. Read through this tutorial on htseq count. See option files, alignment file, GFF file. Those are your options. Please read through this particular this tutorial on this page on htseq count. Read this, and then if you get any errors, you're welcome to get in touch with me. Okay? But I would really like it if first you read the tutorial and try it out the way. Don't use the top HEIC, like now it's going further with the GFF file. I'm pretty sure it's a GFF file. Download your own GTF file from the UCSC Genome Browser. One of the options on UCSC Genome Browser is to select the format here. Right here, instead of bed format, you can select GTF format. Okay?
Yeah.
Right here. And then you just give it refgene.gtf as your format, and then download that file. Again, upload it to the server,
Okay.
whichever directory you're running your program in, and then type this command. It will work. If you have done everything correctly, it will work.
And that command was in the LSF file, right?
That command is right here in the it's right here in the BedTools tutorial file. htseq count minus m intersection strict BAM file, path to GTF file, output file. If you're confused about that, you can always just Google it, and it'll htseq count. The first thing that comes up is this tutorial on how to use htseq count. It's a one-page tutorial. It tells you about the usage, and it works.
Okay.
As long as you've loaded it, it will work. And if you have any errors still, you get in touch with me and I will absolutely help you. Okay? But I want you to try first.
Okay, another question about this.
Yeah.
If you have your sequences and then you want to get the counts for a particular number of genes, a lot of some of these formats or tracks
Okay,
might have.
There is an error with the SAM file then. Because we tried 2 different GTFs. Alright, I'll look at the SAM file. So this is probably then on my end. I'll look into the SAM file. Hopefully your alignments will be different and it should be working with your alignments. If it doesn't, then I don't know, maybe let me look into this error.
Why is it comparing SAM file? You're using BAM file. What's
No, it's saying SAM/BAM. So
Oh, I see.
So HTC, I think it takes the BAM file. It's fine. I have used this in the past. Wait, hold on. Oh no. Okay, so here's the problem. Default is SAM. So
Oh.
okay, simple fix. Simple fix in this entire command, even the one that we used earlier. All you have to do is add one other option, which is minus F BAM. That's it. Okay? That's your fix right there. So minus F BAM tells it that the format for this is BAM. Oh, sorry. I'm going to put this here. And let's see if this works. I will wait for it. And that said, I am going to save this file, the latest one, on our here, bettoolstutorial.sh. I'm going to make it as Friday. What should I call it? Latest?
Friday is good.
Okay, so use this as your guide when you're running this, and hopefully this will run. Let's see. I mean, I don't know. I'm just gonna feel free to take some biscuits with you on your way out.
I have a question. So when we do an experiment, so it's like I want to understand the allele specificity of binding of my protein. Yeah. So if I want to do allele of gypsy, so half the chromosomes from one parent, the half the chromosomes from the other parent, and then so obviously the more or less the sequence is same except for the SNPs or indel, whatever it is. SNPs are there because 2 parents, right?
Yeah.
And then, so basically how do I bring 2 genomes aligned to each other so that I get the same coordinate? And then so that
Why
when
2 genomes?
because we have to use the 2 genomes to align because the reads are coming from both, right? So we have to,
But you're aligning to one reference.
but so one reference, but how are we going to differentiate? Because
By SNPs, by doing SNP calling. On each.
whether, so I'm just curious to know about what happens to the coordinates. If we have the reference genome, it has its own coordinates, and then
You can't have a reference genome. You won't be calling it a reference genome. The reference genome is only one.
yes,
That is the HG38
yes.
that we have created as reference. You will not create your own reference. That might be a separate genome that you want to create. Right? I
So,
mean,
yeah.
so the way you want to differentiate between your parents is that you're going to call the SNPs, and then every time you're looking at your data, you will look at which parent it came from that. Your
How
SNPs
do-
will distinguish.
Yes, if I want to like if this
With respect to
genome-
the reference, right? So they will, for at the same location, wherever the 2 SNPs are different, you will mark that location, and that location will then differentiate between your samples.
Okay, so it is just everything is based on the reference genome.
Yeah, you only have one reference genome.
So,
Yeah.
no, I think it makes sense. It's a very important one to do, but
Again?
it just kind of gave you this weird thing. I don't know.
But
why.
wait, it aligned.
Oh,
Yes.
that's the correct,
Okay.
okay.
Yeah, you just have warning. That's
So,
fine.
yeah, there was one of them. One of them.
So now let's open the aligned the count file.
It's like a gene name with a 0 or 1
Yes.
behind.
Oh, okay.
I think
So
Okay.
this is your,
Yeah,
you
I
know,
got a sense
This is
of-
what I wanted to actually, I'm glad this came up. Like, I hate the fact that it just gives you these numbers and
Yeah.
it doesn't have the name of the gene next to it.
oh, this is because of the GTF has the ensemble. This is the ensemble GTF.
Okay, so if we chose a different
You
GTF,
choose, you could get a different, output.
Yeah.
You get a different output.
this is not,
So it all depends on the GTF, make sure you're using the right GTF.
you know which one?
See, we
And
have
then-
one count here, yay!
Yeah, no, there were a bunch of them that had one count.
Okay.
So one of the things I wanted to give you a heads up on,
Yeah.
you have to make sure that you're using the right GTF.
Yeah, of course.
I think that's probably the most important thing because
That-
you're using something that's link RNAs and then you're matching it up with something that may not, that just might be ESTs or
Yeah.
maybe things
Yeah.
that are just like
Yeah.
coding genes. So-
Which is why we went over the whole UCSC. That's great. That's a great point. So to re-emphasize what Mo is saying, and that is very important, is when you're going to the table browser, we have to make sure that we have the exactly the right GTF. So here, whether it's RefSeq genes you're interested, or GenCode, or retro genes, all of this will just CCDs. All of this will make a huge difference in what you are trying to find. So if you're using link RNA, then that's different from regular RefSeq. Or if you're doing mRNAs, that's different from all mRNAs versus you can use what other mRNAs are there. So like just make sure you have the right one.
So is there like if you just basically have RNA-seq, you just want to know gene X, count X,
Yeah.
what is the kind of most basic one that
So
you
we
would-
use ensemble.